Understanding how the zeros, end behavior, and multiplicity of zeros affects your graph can enable you to draw a quick sketch of a function rather quickly. So let's see how those things are all related. Now look at this first function. I have f of x equals x minus 2 times x minus 3 times x plus 1. So this has already been factored. And since it's already factored, our zeros are easy to find. If we set each factor equal to 0, we would get x equals 2, x equals 3, and x equals negative 1. And each one of these factors is to the first power. So that means the multiplicity of each of these zeros is 1. And what that means is when we reach that 0, the graph is going to go straight through the 0. Now the other thing that we can notice is the degree of this function is 3. We have x times x times x, that's going to give us an x cubed, so this is a cubic function. Because the degree is 3 and each x is positive, so our leading coefficient is going to be positive, we know that the end behavior for this graph is going to be down up. So using those facts, if we want to make a quick sketch of this graph, I know that I have a 0 at negative 1. I know that I have a 0 at 2 and a 0 at 3. I know my end behavior, and I know that my graph is going to go straight through each one of these zeros. So I have a graph that looks something like this. Now, I would have to actually plug in values to see what this max area is and this min area is on this graph. But overall, I have a rough sketch of what the graph looks like. In the second example, we can see that our zeros are equal to x equals 2 and x equals negative 1. X equals 2 has a multiplicity of 1, but x equals negative 1 has a multiplicity of 2. So this is going to be a double root, and that's going to affect our graph. So, because this is really an x squared, the degree of our function is still 3, because in essence we have x times x times x. And so again, they're all positive, so our leading coefficient is going to be positive, so our end behavior is still going to be down up. But when we go to draw our graph, we have a double root at negative 1, and we have a single root at 2. Now what a double root does is when the function goes to the root, it rebounds back off. So it touches the axis, it doesn't actually go through. So if our end behavior is down up, we're going to go up to the double root, rebound off, and then go back through that last 0 to get our quick sketch of our graph. Again, I haven't marked any values on the y-axis, so we don't know how high and low the max and mins are, but we do have a rough idea of what this graph looks like. On our third example, we have x plus 1 cubed, and so the 0 is just x equals negative 1. But this time our multiplicity is 3. That means we're going to have a triple root. When we have a triple root in calculus, this is called a point of inflection. And that is a place where the concavity of the graph is going to change. Now, if we think about the degree for this function is still 3, because we have x times x times x. If we were to multiply x plus 1 times x plus 1 times x plus 1, our leading coefficient is still positive, so our end behavior is still going to be down up. But when we go to sketch our graph, we're going to have a triple root at negative 1. Our end behavior is down up. And what happens at a point of inflection is the graph approaches that 0, kind of flattens out, and then goes on through. So notice that to the left of negative 1, our graph was concave down. To the right of negative 1, our graph is concave up. And that's what happens when we have that higher powered odd degreed root for the polynomial. It's going to flatten out at that 0, but still go through the 0. So when we have an even degree and the multiplicity is even, the graph is going to rebound off the 0, and if we have an odd multiplicity, the graph is going to go through the 0, but the higher power the 0 is, the flatter it's going to be when it reaches the graph at that particular 0.